All right. Hey, everybody. So topic 19 today. Again, a reminder that you should get your blog done by this week. If anyone still has any questions about that, please let me know. I'll be looking through submissions towards the end of the week or start of next week. So you don't have to write more than 500 words. I've already told a couple people as well, if you have like a big topic that you would like to write a blog on, you can split it into a couple parts, like write half of it for this phase, half of it for next phase. If that's of interest to you, feel free to do that. So you don't have to write like, you don't have to think of like new big topics each time. All right. So today we're getting into multiple regression and model validation. So yesterday we kind of introduced linear regression, which we did in the context of just one variable. We were using just height to predict weight. And today we're going to expand on that and also talk about a little bit of model validation. Another way to check for how do we know our model is good or not. Yesterday we had R squared, and today we're going to look at some other things. All right, so I've already imported our libraries, everything we've seen before aside from Scikit-Learn. So Scikit-Learn is actually something that we're going to get very, very familiar with in the next phase, but we do get introduced to it a little bit this phase. So I'll show you all Scikit-Learn later on. Before we get into multiple regression, wanted to kind of like round off where we left off yesterday with our height and weight data set. So we built that model yesterday, see how we had our R squared of 0.955. We also determined that, there's a relationship here between weight and height, that every 1 inch increase in height leads to a 5.539 increase in weight based on our model. And also these two parameters of intercept and height are both statistically significant. So based on these 20 data points, this model is doing pretty good. All right. So first, let's talk about making predictions. We talked about, I mentioned that modeling, you kind of have two main things that you can do with modeling. One, learning about your data, which is what we did yesterday, but two, also using our model to make new predictions. So within stats models, making predictions isn't as straightforward, but I'll show you how to do that nevertheless. All right, so here we have our data frame, our weight, our height and weight. The way that stats models does it, you have this dot predict function. What's a little bit finicky with this dot predict function is for some reason it has to take in a data frame with the same number of columns as your training data, as the data that you fit it to. So therefore, what I'm going to do and how this will work is I'm just going to pull out one row of data and I'll feed it into the dot predict. So you can see here, the actual value of weight was 192. And the predicted weight was 188.78693. So this is our Y hat, and that is our actual Y. So I set up just this like really quick, I guess, cell of code to just check for predictions. This is just based on the index number. Of course, you can do this in a much nicer way. Let's say I just want to see the 6th person, actual weight is 195, predicted weight 194. That's pretty good. I know there's 20 in this data set, so 135, 133. I think it can go up to 19. You can see that there's a bigger difference there. So that's what we can do for using stats models built in .predict. Another way you can do it is just by manually using the coefficients. If you know the equation of the line, which is what I'm using here, you can write a function that predicts weight using height. So here you can see that I'm actually putting our coefficients here, our y-intercept and our slope value, and weight is equal to this times height, minus 204. Oops, what did I just do? Okay. So with that, any height value that I put in, I can predict weight. So with a height of 60 inches, this is the predicted weight. If I have a height of, I don't know what, I get confused with inches, but 55.8 as an example, you can get a prediction for pretty much any weight value. So that's one quick way that you can make predictions on any random height. You can get the predicted weight for any random height that you feed in. That's one way that you can do it. Typically with these like dot predict functions, the reason why we're going to talk about that other library, Scikit-Learn, is because it has a much easier to use predict functionality, which I'll show you all towards the end of this. So this kind of rounds off our like one variable regression. Any questions before we get into multiple? Okay, So with multiple regression, I would like to use our car data frame that we are fairly well acquainted with. Our car data frame, we're going to basically predict miles per gallon with all of these features. And a lot of the assumptions that we talked about yesterday still hold. So the linearity assumption, that still holds as well. And I'll actually talk about that in a little bit. I think I talked about this yesterday, I forget. But if you want to do a multiple regression, it's the syntax for running your OLS is very, very similar. Just for each new variable, you just add like a plus in between it, and it recognizes that that you're going to use that column. So one thing to note, models do not take in non-numerical columns. So something else that you can look at when you're doing your EDA, you cannot have non-numerical columns. Also no NaN values, no null values. So think about how you're going to fill those in. And then also if you have non-numerical columns like this, you can do categorical variables, which I'll talk about right after this. So just to show how the formula works, I'm putting in every column except for car name here. And we have this model, just like that. Your model is built. A couple things to note. One, we have our R squared. I know we had our really good R squared of 95.5 for that last simple linear regression that we did yesterday. Now our R squared is at 82.1, which is a little lower, but basically that's saying that the variation in miles per gallon, 82% of that variation can be explained by all of these features, which is, I think, not bad. Like, how would you predict miles per gallon using only these features of a car, right? Like, I feel like a car has a lot more aspects and characteristics to it that can affect miles per gallon that aren't being introduced here. So this is where we talk about adjusted R squared. So adjusted R squared, there's like a whole mathematical proof behind this, but basically what will happen is I just said that there are a lot of features that we're not considering that could affect miles per gallon that we're not using yet. So you might say, okay, why don't we add those features? Assuming that we can get that data, let's just say we're adding 10 new features and we have no idea if they're going to be effective or not in helping us better predict miles per gallon. Something about R squared is naturally, the more features you have, R squared is just naturally going to go up. It's just naturally going to get higher and higher. So adjusted R squared kind of takes that into account and kind of readjusts your R squared, because naturally with more variables, your R squared goes up. So adjusted R squared kind of takes into account the fact that, okay, you have a lot of features, therefore your R squared should actually be a little bit lower. There is a calculation for that in one of your labs, but for our purposes, we really don't have to make that calculation. But that's what the adjusted R squared is all about. If you have a lot of features, and it's possible to have like hundreds and thousands of features in a linear regression, we definitely won't be doing anything to that scale, maybe. But in those cases, when you have a lot of features, your R squared will naturally be very high, and your adjusted R squared will adjust it down to a number that's a little bit more like apples to apples comparison. All right, also what we have here, we have our different coefficients. Cool. So basically this is saying that every one cylinder that you add, miles per gallon goes down by 0.44. Every increase in acceleration brings miles per gallon up by 0.15, so on and so forth. Now you can see that p-values, yesterday our p-values were all at 0, but in this case, we have a couple non-zero p-values. So how do we interpret that? So this one is the highest one for cylinders. We have a p-value of 0.167. Now that just means that there's a 16.7% chance that cylinders has this relationship with miles per gallon just by random chance. So we're just saying that this relationship between cylinders and miles per gallon of negative 0.447 is not statistically significant. And so what do we do in this context? Usually, because there's no significant relationship here, we either try and transform cylinders, which I'll talk about in a little bit when we talk about transformations, or we just don't use the feature at all, because the feature, if it has a high p-value, doesn't really contribute to the effect on miles per gallon. So that's one way that you can think about it. It's just insignificant variables. when you're doing your project, your final model should not have any p-value that is above 0.05. So maybe in your data set, you've got like maybe, I don't know, 15, 20 variables. None of them should have a p-value of above 0.05. There's also nothing wrong with dropping a bunch of variables and only keeping ones that are significant. That's actually a very common practice. But also, when you're dropping these variables, and we'll talk about that during our office hours next week, there are some implications to doing that. So we'll talk about that when we cross that bridge. So that's just a simple multiple regression. You'll see that doing this regression project is going to be extremely iterative. If anyone has been working through the labs already, it's not as simple as, yeah, we can just do like our model.fit, model.summary, interpret. Based on these results, we're going to keep iterating over a modeling process, and that's really what our projects are going to be looking like. Tomorrow's session, I'm going to be going over like the structure of a project, following our project 2 guidelines. So happy to talk about any more like project related things then. But yeah, any questions about like this stuff so far? Okay, so the next thing I want to talk about is categorical variables. So what is a categorical variable? An easy way to see if it's categorical, usually if it's in some sort of string, it would be categorical because it's just not non-numerical. But you can see here we have these other variables like origin, number of cylinders, could be categories. And so there is one way to look at it is to basically plot your scatter plots. And I basically separated it into what I think are categorical variables and what I think are continuous variables. So these blobs kind of look more continuous, right? So these are definitely continuous variables. You know that the values for acceleration, displacement can range, can be any value between those ranges. Now with these variables, it sometimes can be up to your, you can sort of make that decision yourself. So for example, cylinders, I decide, okay, this should be a categorical variable just because there's no clear linear relationship there. I don't know if that makes sense. I would say for year, even though each car can only be in a specific year value, if you think that miles per gallon is affected by the change in year in a linear fashion, you can keep that as a continuous variable. I feel like I just went in like a whole circle, but does anyone have anything to clarify about that? Okay.
So you're essentially saying that unless you're trying, that it's more of a categorical variable unless you're trying to do, say, an analysis saying that as the years have gone on, the miles per gallon of a car has gotten better in, say, that scenario, and you're trying to prove that by going miles per gallon per year, rather than just a blanket look at those two variables.
Yes, correct. Exactly. So something to note is that all of these scatter plots, I should have said earlier, that all of these scatter plots are the X variables with respect to Y. And so, yeah, going off what Justin just said, one example, we can see here that year kind of like follows this straight line going up. So you can see that there's a fairly linear relationship there. Cylinders, I'm going to exaggerate this a little bit, but the relationship between cylinders looks kind of like this. And so because it's not like a straight up linear, it might make sense to treat this as a categorical variable. In this case as well, it maybe isn't super clear with origin, but like there's a slight upwards. But imagine if, I also don't even know what origin means in the context of cars, but let's just say that the data points were very much clustered around here for 1, here for 2, and here for 3. That's a very clear sign that you should turn that seemingly numerical column into categorical variables. And what that has in terms of an implication on your model, we'll see in just a bit.
Okay, okay, so then when you're looking at that, if you're doing miles per gallon versus year, it kind of does you can kind of see that it does improve year upon year, but that would be something that if you were isolating that particular instance, you'd focus on that, but otherwise you could just say it's kind of categorical anyway.
Yeah. And this is also something that you can test out. Let's say you do have a variable like year that could be continuous, could be categorical. Maybe run the same model twice with one as year as continuous, one with year as categorical, and see how that affects your results. I'm going to show you all what it looks like when I have categorical variables, because the way that you interpret it is similar, but it's slightly different. All right, so the method that you can use to turn continuous into categorical variables is known as get dummies. So a categorical variable, actually, let me just do this and I'll show you what that looks like. This is what a categorical variable looks like. Very similar to, remember that movies project when y'all were trying to figure out genres? Very, very similar to that. There's this get dummies function that basically for each cylinder value, it will make a new column, and then the values will be ones and zeros dependent on whether it is that cylinder value or not. And same for everything else. So as you can see here, the number of columns that I have explodes from, what was this? 6? No, I had, yeah, I think I had 1, 2, 3, 4, 5. I have 6 variables, and here I have 23 variables. So it just exploded because there are a lot of unique years. I think there's like 5 unique cylinders, 3 unique origins. Something else to note is that I am dropping first. This drop first thing I'm going to talk about right after this. But typically, when you do dummy variables, you have to drop one of them, and I'll talk about why that is right after this. But these are what dummy variables look like. Basically, it's a representation of categorical variables numerically. It helps for when you have strings as your values, and it also helps for treating, if you don't have a linear relationship between values, sometimes doing categorical helps. So let's just plug this into our OLS and see what that looks like. So here you can see the columns. I have like cylinder 4, 5, 6, 8, all these different year values and the different origin values. For the formula, because I don't want to type each of these individually, you can use a dot join to throw that together. So you can see here, I have my formula generated just by doing a plus dot join. And let's fit our model to see what that looks like. All right, so our R squared, this is what, 784. Before we had 821. Just naturally, see, just by adding all of those new variables, our R squared went up. And adjusted R squared doesn't go up by that much. 818 here, 867 here. But in looking at this, it becomes a little bit harder to read, but I have a lot of insignificant variables. Let's talk about the coefficients first. As an example, we have cylinder 4 here. Now, the coefficient for a categorical variable, if you think about it, it's kind of interpreted the same way, but it's sometimes hard to think about. Basically, this is saying that if the car has 4 cylinders versus not having 4 cylinders, the miles per gallon will go up by 6.939. And if you remember, we dropped first. So actually, there's another categorical variable that isn't represented here. That's cylinder 3, I believe. Let me just check real quick. Yeah, there was like a cylinder 3 that is not represented in our list of coefficients. So that will kind of be like our baseline. So everything held constant. If we want to compare cylinder 3 to cylinder 4, there's an increase of 6.939. If we want to compare cylinder 3 to cylinder 6, there's an increase of 4.297. So it's a little bit harder to think about because now you have this like baseline cylinder value that's within the model, and it's actually captured in the intercept term. If that doesn't make any sense to you, that's fine. But they're just saying that that's how you will interpret this number. Basically having 4 cylinders versus 3 is 6.9399. And you can say that because at any one time, a car can only have one of these cylinder values, right? If it's 3 cylinders, these cylinder values will all be 0. And if it was 5 cylinders, this would be 0, this would be 0, this would be 0 as well. So a little bit trickier to interpret, but that's how you do it. Same for years. You can see here that I think the base year was 70. Yeah, I think it should be 70. If a car was made in 72 versus 70, miles per gallon goes down by 0.49. If it was made in 81, miles per gallon goes up by 6.4582. And same for the others as well. Questions about interpreting these coefficients?
Okay, so you're interpreting it from the dropped category.
That's
why
right.
you drop it, so that because you needed something to some starting point.
Mm-hmm. Yeah.
So okay, so that then you have to remember that there's a dropped column, that dropped category.
Yeah.
And then the number is related to that one, not the one above it, because it's their category. It's not continuous. It's just like, say cylinder 4 is just 7 plus whatever 3 was, plus 7 above what 3. Okay. All right.
Yeah. Yeah.
So if you're looking at the P coefficient here, if you notice, like some of the years, it looks like it's not statistically significant. So if you wanted to improve the model, would you just remove those years and then try again?
Yes, absolutely. So because now we've sort of separated each year value into, I don't even know how many there are here, what, 13, including the 70? Because we're considering the 13 years separate, they can kind of be treated as separate columns. And so, yeah, we have a lot of insignificant variables here. Like, for example, acceleration's p-value went all the way up to 0.967, which just goes to say that, yeah, there's definitely no relationship between acceleration and
did that happen because we then broke down the rest of like the cylinders and years, and because it was able to sort of like, yeah, focus in on those and see where things were happening, it showed that acceleration. Okay, thank you.
Yeah, that's a good point. Every time you refit your model on a different set of features, the coefficients change, the p-values are going to change, because it's going to see like, oh yeah, okay, in comparison, this feature is not useful at all in helping us predict miles per gallon. So yeah, as a result, you'll see a lot of the p-values change, which is why I say it's very iterative. Let's say I decide to drop every p-value above 0.05. I drop all those p-values and I rerun the model again. Very likely, or not very likely, it might be the case that refit on this new subset, you have again insignificant p-value. So it's kind of an iterative process. And I'll talk about how we are going to do that with respect to our project tomorrow. But yeah, absolutely right. These p-values change because we've refit our model. Now, there's something that people commonly ask is, because let's say out of all these years, like, let's see, 1, 2, 3, 4, 5 out of 12 of them, 5 out of 12 of them are insignificant. Now, does that mean that I should not use year at all, or can I just use the significant years? So basically the answer is you can just drop the insignificant years. Having high p-values for years 71 through 75, that's just saying that whether a car is made between 71 and 75 has no effect on the miles per gallon, or like has no statistically significant effect on the miles per gallon. However, when a car is made in the year, actually this one is also not very significant, but okay, let's just say, but a car being made in the year 77 is significant, and all of these other years, those years are significant. You can sort of treat each year as a different trigger.
There may have been some legislation, I think, in 76. I think it was after the gas crisis, and it like became mandated that cars started to have like a higher miles per gallon. So you can also like kind of look at it through a historical lens, but yeah.
Yeah, that again, like if you have contextual knowledge, that honestly helps a lot. Like I've been looking at I've been doing capstone projects for other students, and every time there's a student that like does a project that they have strong like existing knowledge on, or contextual knowledge on, or like expertise in that field already, always have they always have a lot of really good interpretations or really good reasoning for why they're seeing what they're seeing. Yeah, absolutely. So yeah, this is what we do with categorical variables. Basically, if you see that, okay, let's just say year 71 through 76 are insignificant, let's just go into here. Let's see, what's an easy way to do this? All right, I'm just going to copy this over and we can rerun our model using not the insignificant years. This is a very clunky way of doing it. So y'all are going to do it in a much better way than I am right now. But let's do this, f equals this. And then let me just pull our model summary here. Oops. Oh, wait. My bad. Okay, there we go. Formula equals to f. All right, so I refit my model here. As you can see, I dropped, well, acceleration is still high, but I dropped all my insignificant p-values. Usually when you drop insignificant variables, your R-square doesn't get affected by much. You can see that it's only gone down by 0.004. When you have insignificant p-values, usually it's because, well, the thought behind taking away insignificant p-values is twofold. One, it's unnecessary computation for your model. And so if you have a lot of features and a lot of rows, your model will take unnecessarily long to run. Of course, with these smaller projects, it's not going to be a big difference, but that's a big reason. But also redundancy, which I guess is kind of on the same vein, but there's some mathematical redundancy, which is actually the next thing that I'm just about to talk about. So yeah, you would do this iteratively. Based on this, I'll probably like think about dropping acceleration. Maybe I drop, actually, let's try that. Let's drop acceleration. You can see without acceleration, it looks like displacement is up now. All right, let's get rid of displacement. And like that, everything becomes significant again. And so now I know that in our model, I only need to use this data to predict miles per gallon. And it still has a fairly okay R-squared comparative to where we started. Cool. All right. So the next thing I want to talk about is multi-collinearity. So that's actually another assumption of linear regression, specifically for multiple linear regression. We couldn't really talk about this yesterday because this doesn't really apply to when you only have one feature. But the idea of multi-collinearity is if you have two X features that are collinear, that means that they're highly correlated with each other, you don't want to have that in your model. The idea behind that is, and let's actually take a look at things that are multi-collinear. Ooh, yeah, so we can do this. I have our original data set, and I do a .core, which is a pandas function that shows you the correlation between every variable with every other variable, and it's in a matrix form. So for example, let's see, weight and displacement have a very, very high correlation. Weight and displacement are 0.93 correlated, which means that however weight moves, displacement moves very closely with it. So what does that mean in terms of when we are trying to predict miles per gallon with both of these features? It's just redundancy. So imagine we get some coefficient for weight. And in this case, we have a coefficient of negative 0.0045. So I'm going to just assume pounds. So let's just say that every pound weight increase, miles per gallon goes down by 0.0045. I initially took away displacement because it had a high p-value, and that's actually they're kind of interconnected when you have high p-values and multi-collinearity. Because weight and displacement are correlated with each other, why do we need to account for both when we're trying to predict miles per gallon? So that's the whole idea behind why multi-collinearity is not desired, because it's redundancy. The model's getting confused of like, okay, should I prioritize one over the other? Usually when you have multi-collinear variables, or basically any variables that have high correlation with each other, you want to usually drop one of them. So in this case, you can see that we have a bunch of really high correlation values. So we have like 0.93 over here. We have 0.89. There's no set threshold for how much is too correlated. That's kind of up to you to tune and decide iteratively. But yeah, based on this, I'm going to say, all right, let's drop a bunch of variables. But first, I'm going to first check for linearity between the target and features. So what I'm doing here is I'm looking at this. So data.core, let's look at the miles per gallon column, because remember the miles per gallon column, that's what we're trying to predict. Multi-collinearity, we don't want multi-collinearity between the features and themselves, but we still want each feature to be somewhat highly correlated with the target. So it's kind of two different correlation things that we're checking. So first, we want high correlation between miles per gallon and everything else. So you can see here, we have some things that are not very correlated. For example, some of these years, as you can sort of see, like the insignificant years have pretty low correlation. The higher years have a little bit stronger correlation. So let's just set a arbitrary threshold. I only want to keep the features that at least have a 0.3 correlation with our miles per gallon. You're going to do this in a much more iterative way because this is just going to cut out a lot of features right off the bat. So just like that, I'm only going to keep these features: displacement, horsepower, weight, acceleration, 4 cylinders, 8 cylinders, these 2 years, and origin. This is just me setting a threshold. If you want to do it in a less destructive way, you could probably start at a lower number and cut it out slowly. But let's just do 0.3 for now. All right, and then I'm going to let me see. I forget what I did at step 1. Okay, so these are the columns that I'm going to keep. So I'm just going to rerun my OLS model first with only these features. Oops, what did I just do? Is it this one? Okay, cool. So with these features alone, we got a pretty decent R squared still, but we still have some insignificant features. So let's just look at multi-collinearity and figure out whether that's something that we can do, or that's something that we have present in our data to make our model perhaps do a little bit better. All right, so let's just take a look at the data that we have left and look at what is correlated. Now there's this other code that I have here, and this comes from one of the labs. I actually think this is really neat code. But before we get into that, we can sort of see, all right, weight and displacement have that high correlation we were talking about, horsepower and displacement too, even acceleration and displacement having, and this cylinder's, oh yeah, here we have like 0.8 correlation here. So these high values are what we do not want. So this is a quick way that we can weed out what is correlated with each other to figure out what variables we want to drop. Okay, so a couple different things going on here. First, you can create the correlation pairs. A lot of different methods being stacked over here. Feel free to break it down to figure out what's going on here. And this correlation table looks like this. We have variable 1, variable 2, correlation amount. Any variable with itself has a perfect correlation of 1, but this is going to go through all, I guess, 100 combinations of our 2 variables and their correlation coefficient. So next, what happens is we kind of put them together and figure out what the correlation coefficient, get rid of the 1s as well. And we figure out, okay, which are the highly correlated pairs? So highly correlated pairs, as we saw earlier, weight and displacement, horsepower, displacement, weight and horsepower. So these 3 are basically all correlated with each other. So maybe we want to drop 2 out of 3. Cylinder 8 also turns up a good bit at the top. Weight here as well. So this process of deciding which one to actually drop is really up to you. There's a lot of ways that you can benchmark and test this, but for our purposes, let's just keep horsepower, acceleration, cylinder 4, 80, 82, and origin 3. So this is our data set. Again, run this formula and fit our model. So because we dropped multi-collinear variables, and remember, I decided to get rid of weight and displacement instead of acceleration. Acceleration now has a 0 p-value, whereas before, I remember acceleration was the one with a high p-value, and it's probably because of the redundancy between displacement, weight, and acceleration. So you can see both acceleration and displacement have high p-values, mainly because I think it might have been looking more at the weight variable in this model. But yeah, if I were to replace acceleration with weight, I think we will see that I think they should be fairly, yeah, we still have good statistical significance throughout, just because, you know, weight and acceleration are just highly correlated with each other. So they kind of have the same effect on miles per gallon. questions about that? Okay, so that is the whole idea of multi-collinearity. So we don't want features to be correlated with each other because it just leads to redundancy in our model. All right, cool. The next thing we're going to talk about is transformations. So remember how we talked about the fact that in linearity, we want our target variable to be correlated with our features. So I actually don't want to use this graph. Let me pull a different graph down. That's a little bit more. Yeah, let's pull this one real quick. Okay. Sweet. Okay, so we have these. 3 of these look like they sort of can be linear, but I feel like it could be a little bit more linear. It kind of still looks a little bit curved. And so there's several things that we can do to make this relationship look better. And there are many kinds of different transformations that you can do. I'm going to break it up into 2 different sets of transformations. So 1, there's a transformation that changes the distribution of your values. And 2, there's just rescaling. So both of these are subsets of transformations. For our purposes, the most commonly used transformation to change the distribution of our values is log transform. So this is what a log transform is. And hold on, let me just see how we can plot this. All right. And the idea of a log transform, it helps to linearize your data a little bit better. Basically, it takes the low end and the high end of your data and reshifts it so that they're more evenly spread out. If anyone is familiar with like the log distribution, it would make sense, but let's just see the effect on taking the log value of all of these features. So what I want to do is this. Let me see if this will work. Zip, blah, blah, blah. X column. I might have to recode some of this, but all right. Basically, we've log transformed these, and I want to really quickly change this data log so that we can see how different that looks. I think that's going to break. There we go. Let's see, what's it called? Log displacement, log horse, and log weight. Actually, let me just do plt.scatter of which one was displacement and weight. Okay, sorry, bear with me a little bit. This, and then we want to look at data, MPG, I think car DF. All right, there we go. So initially, our relationship between displacement and miles per gallon looked like this curve here. By doing the log transform, it now looks a little bit more linear. So that's something that you can do to your data to achieve linearity, which is pretty neat. So this is displacement. Let me just move this upwards so we can directly compare. This is displacement. Let's look at horsepower. Horsepower is called log horse. With log horsepower, what looked like that before now looks a little bit more like this. And then weight kind of already looks linear. So let's just see what that transformation has done. And oops, weight is log weight. And log weight, you can see a little bit more linear than it was before, even though it was already pretty linear. So log transformation is something that you can do to your data to help achieve its linearity. Now, when you're doing a log transform, let's just say that between all of your variables, you kind of have this shape over here. You can either decide to log transform just each of the X variables individually, but if you want to be a little bit more, I don't know, efficient, I don't know. You can also choose to log your miles per gallon if you'd like. You can choose to log your target variable too. The only difference is in interpreting your coefficients, you're going to have to interpret it differently, which is what I'm going to talk about in a little bit. So I'm going to talk about interpreting those coefficients in a sec, but basically log transformations is something that you can do to your data. And so instead of plugging in horsepower, I would plug in log horse. And instead of weight, I'll plug in log weight. And then I would get different coefficients as well. All right, I'll get into the interpretation in a little bit because I want to talk about the other transformations first. So there's a bunch of different transformations that do not change the distribution of your data. By distribution of your data, I mean the shape of your histogram. So we had these shapes of your histograms here that look like this. Any of these transformations, and I'll go into them in a little bit more, when you do any of these transformations, like for example, you can see that, let me actually move that one down as well. Oops. Let me move this here. Okay. So we look at the original log displacement and the displacement here. Let me go a bit outwards. Sorry about that. Okay, so we have displacement and log displacement. This is displacement. This is the log displacement scaled. You can see that the shape of the histogram does not change at all. However, when we did a log transform, the shape of the histogram did change. What did change, however, if not the shape, is the scale of your data. So you can see here, what we originally had was log displacement between like 0 and 6. But here our displacement is now between like -2, +2. Displacement went through a, I think displacement went through a normalization. So there are these sets of transformations that do not change the distribution of your data. And I'll talk a bit later about why we want to do that sometimes. Okay, so different transformations you can do. Min-max scaling. So min-max scaling will take your data and force it between 0 and 1 based on where your minimum and maximum values are. That's the formula for that. There's also standardization, and standardization, if you remember, is same formula as our z-score. So you can get the z-score of your data points. And also that also does not change the shape of your distribution. There's also mean normalization. That one is used a little bit less. And then unit vector transformation is also used less. Usually the ones that are used the most, min-max scaling and standardization. Between these two, there's also a difference between these two. Min-max scaling forces your values to be between 0 and 1. So if you have like a min-max scaled, data, it will always be between 0 and 1. This is 0, that is 1. Now, when you have standardization, if you remember from z-scores, it does it based on how many standard deviations away from the mean you are. And so this is centered at 0, but it's not bounded. Your values are not bounded by any numbers. So let's say you have something that's already kind of normally distributed, but not standard normal. This just turns into the standard normal distribution. Again, if your data initially looked like, I don't know, this shape, you would have this shape, but around your standard normal. All right, let me just undo that. Now, why is it important to know what is bounded and what is not bounded? One thing to think about to choose like whether you want to do this transformation or this transformation, think about outliers. So if I had like a bunch of let's just say I have one really, let's just say I have one super heavy car, so very, very high weight. If I had a distribution like this, my data will sort of look like this, and then like one tiny bump here for that high weight car. And this number, based on the standard deviations, maybe that's like 5, because maybe that's 5 standard deviations away from the mean. Now, in this scenario, where I have a min-max scaled value, what will the outlier do? The outlier will actually still force everything to be between 0 and 1. So it will force this to be our like 5,000 weight car. I don't know, I made the number up. But basically our values will be very skewed. Most of our values will likely be between like, I don't know, 0 and 0.3. So this is good, something that's good to think about. If you have a lot of outliers, how that might affect your scaling. Because this min-max scaling is bounded and standardization is not bounded. Questions about that? All right, well, mean normalization and unit vector transformation are also both bounded. They're also both bounded methods. Okay, so let's just do a bunch of transformations and see what happens. Here we have scaled acceleration, displacement, weight, and horsepower, all with different methods. And let's take a look and see what happens when we run that through our regression. So let me actually change this real quick. Let me just see what data is so I can add it there. Okay, cool. So I'm gonna just change this to data. Oops. All right, so that's just gonna add everything there. And then we're gonna add this as well. Bear with me as I make these quick edits. Okay, so I have this done. Data should now have, why does it not have all our other things? Sorry about that, y'all. Okay, never mind that. Basically, when you scale your values, imagine that these, instead of weight, let's just say you're doing your log weight. Instead of weight, if this was log weight and you get this coefficient, you interpret it slightly differently. You interpret it as one increase in the log of your weight leads to a negative 0.0036 effect on miles per gallon. So if you know that log weight, a +1 in log weight leads to a negative 0.0036 of your miles per gallon, how much does weight actually affect miles per gallon? You have to do a reverse transformation. So if you want to see how much actual weight affects miles per gallon, you would actually have to take the exponent on both sides. So a change in weight should lead to exponent of negative 0.0036. And then you find out what that number is, and that is your relationship between your variable and your target. So basically, you would have to reverse the transform. Similar to when you are doing the non-distribution changing ones. Basically, if you have like a standardized weight, so standardized weight, a +1 is standardized weight leading to whatever effect on whatever it is, you would have to reverse that. And any of this scaling is a little bit harder to reverse. However, I also want to say, why would people do this then? So imagine we are trying to study the effect on miles per gallon by all of these features, right? Let me actually go to an example with more. Let's go up to this one that we had here. Okay, so let's just say we wanted to study the effect of these features on miles per gallon. And we want to find out what the most impactful feature is. However, you see that like weight, if we were to just look at it like this and we see, all right, well, the highest coefficient means it's the highest impact on miles per gallon. That's one way to look at it. Cylinders at, is that the highest one? Yeah, cylinder at 8.6272. That gives us the highest coefficient. We can say, all right, having 8 cylinders has the most effect on weight. That is something that can make our, that can increase our miles per gallon as much as possible, just by giving it 8 cylinders. However, you're failing to see that horsepower and weight are measured on different scales than all of these dummy variables. Dummy variables are all measured from 0 to 1, but horsepower is measured on, I don't know what kind of scale horsepower is. Yeah, 50 to 200. Weight is 2,000 to 5,000. And so the effect of a unit increase in horsepower and weight is definitely not going to be, like, these coefficients are understandably small because an increase in 1 horsepower is not going to affect the miles per gallon by very much. And so that's one of the motivations for scaling all of your variables. Typically, you don't do something like this. You typically do not do different scaling for each variable. I think like this is what they did here somewhere. Let's see, where was that? Wherever it was, you typically do not do different kinds of scaling per each variable. You typically scale most of your variables the same way, depending on what your data looks like. But let's say we scaled displacement and horsepower and weight such that they're all min-max scaled between 0 and 1. And with that, with it scaled between 0 and 1, we know that they're now on the same scale as all of these dummy variables. And so that will allow us to more directly compare allow us to directly compare the impact of each feature in a more apples to apples manner. because now we're measuring everything on a similar 0 to 1 scale. I know there's a very like roundabout explanation. Does anyone have any questions about that? Okay, then the question now I have is, then should you scale your data or not? I will tell you that if you only scale your data in a way that that doesn't impact the distribution of your numbers, if you just, let's say you standardize all of your values here, your R squared is going to stay the same and your P values are going to stay the same. The only thing that will change is your coefficients. And so what sometimes people do is have a version of your model that is scaled and a version of your model that is unscaled, just so that you can do either the comparison between variables, or you can just do the direct coefficient interpretation where you don't have to reverse transform everything. But that's something that we'll talk more about when we talk about the project next week. Okay, any questions about that? All right, we're a little bit low on time. Hopefully you'll finish this. But the last thing I want to talk about today is model validation and regression in Scikit-Learn. And we're going to talk about this idea of train test split. So far we've been fitting our models to our data, like we fit a bunch of regressions today already. And evaluated our models by calculating the errors between our y hat and our actual targets y. We talked about that in terms of like the residual plot yesterday, which you can do the same thing for with a multiple regression as well. And we also can evaluate our model by using R squared. So, however, the reason why we're building a model is typically to not make predictions on data that we already have. We want to be able to use our models to make predictions on data that we don't yet have. Like when we did that height and weight model at the very top. When we made this height and weight model, if we already know these heights, we don't need to predict these weights, right? We more likely want to do something like this, where we can give it any height amount and figure out what the associated weight should be. So ideally, that's what a predictive model is used for, right? That makes sense. Why would we need a model for data that we already have? And so because of that, we have to check for over and underfitting. The problem of over underfitting, you can go on and on talking about like the implications of all of these things, but basically there's over and underfitting. Looking at these three examples, there is underfitted data where your data is like this and your line just does not fit through your data very nicely at all. There is like a pretty okay fit and there's overfit. So what's the issue with each of these? When you have underfit data, your model is just not predicting anything well. If you have overfit data, you can see this squiggly line over here. And basically any prediction that you make is on this squiggly line, right? If I had a data point that was, let's say, over here, which seems reasonable, given all these green dots, there will be this error of prediction where it shouldn't be. Because if I like do the same thing over here, and this point was over here, the prediction is a little bit better. So there's this whole idea of over and underfitting your data. The idea is here is you want to have your model be generalizable to whatever you want to use it for. So that's why we do a train test split. When you have enough data and you want to build a predictive model, what a train test split does is you take all of the data you have and you take usually 20% of your data and you pretend that that is unseen data. And so when your model fits, it only fits on the 80% of your data. Now, based on the model fit to your 80% of data, you can test how well your model generalizes to unseen data by using your test set. And there's a couple ways that you can do this. We'll look at training errors in a bit as well. So let's just run this full full process here. Let's just do all of these all of these transformations, and we end up with data that looks like this. And we're going to run this through our model. We can do this in Scikit-Learn. You can do this the same way in stats models that we've done above, but Scikit-Learn is a lot better tooled for doing this train test split thing. So different ways that you can incorporate this into your project. I'll talk about that tomorrow. But basically, with data here, we have our final data. let's see, we have our y and x. For Scikit-Learn, you do have to separate your y and x's. So y is here, our x's are here. I guess for now, we're just going to use these. And what we're going to do is we're going to split our data. And so from Scikit-Learn, which is a library that we're going to use a lot more in this next phase, within Scikit-Learn, there are all of these methods that are built in to help us do this like splitting process. So we just feed it in our x and y. Test size is 0.2 because 20%. And this will actually split all of our data into 4 sets. So with these 4 sets, what do these, oops, what did I just do? I think I deleted this cell. Edit, undo, delete cell. Okay, there we go. So what does this split do? We take a look at X train now. We have 313 rows where before we had 392, and they sort of like randomly shuffle our data around. If we look at our Y train, our Y train is the same way, 313 rows. We're going to basically fit our data on X train and Y train. And then we have our X test, which are these 4 columns, sorry, X test, these 4 columns, 79 rows of the holdout set of data that our model is not going to see. And then when we run this through our model, it'll give us a bunch of predictions, which we will then compare to Y test to see how closely it's predicting. Questions about that process? I think we're going to go a couple minutes over. Okay. So this is how you do it.
Hold on a second.
So, oh, yes.
So the test values are the ones that you are, so the train is the one that you're using to predict, and the test is basically your control, essentially, if you're thinking it from experimentation.
Yeah, you can sort of think of it that way.
Yeah, so X is basically the values that the X train or the Y train values are essentially the experimental values that you're feeding in to try to predict something. And then the test values are the ones that you're essentially your control group, you would call it, that you're using to see if it still fits. Correct.
Yes, yeah, exactly. You can think of it that way. Absolutely.
Okay.
Cool. All right, so as you can see in these lines of code, I'm going to talk more about this later this week and this syntax and what's actually going on here. But we're going to use the same model just in a different library, which can be a little confusing. But basically, stats models, which is what we were running earlier, has their OLS, and Scikit-Learn has its own version of linear regression as well. They actually use 2 different methods of solving it, but results usually about the same. So first, we're going to create an empty model. So this is known as the process of instantiation, which I'll talk about more another time. But we're instantiating this empty model and then fitting our X train, Y train data. So after that is fit, we can then make predictions on our X train and our X tests. And why we're doing that, we'll see in a little bit. And as you can see here, I put Y hat train and Y hat test. So Y hat train is an array of values that come from predicting on this train set. So imagine when we had our, let's go to an example over here. When we had our weight and height over here, and we had our line that goes through it, we're basically good. This is our Y hat compared to our Y train. So that's what we're doing. All right, back down here. Okay, so now that we have our Y hat train, we also do that for our Y hat test, because we can use this dot predict function on any array that matches the same shape as our input data. We're then going to use mean squared error. I hate that there's a typo here. Sorry, mild OCD acting up, but okay. Scikit-Learn has a mean squared error method that basically compares the error between 2 arrays. And so when I just run this code real quick, you can see that the train and test mean squared errors and root mean squared errors are pretty close. So you can see here, this is squared. So let's just look at this regular value. Root mean squared error for our train set is 4.097, basically about 4.1. This error is basically the average error between the line and our data points for our train set. Now, this is actually pretty impressive because our test error is a little bit lower, which is kind of rare, but our test set error is a little bit lower, which is not often the case. Usually it's a little bit higher. But anyways, having a very close error value for your train and your test set is good. That just means that your model, which was only trained on your train set, can still make predictions on data it hasn't seen before. And that's the whole idea of why we're doing model validation. Because if you just fit your model to your data and you don't check for, and you don't use a test set to check, you don't know how well your model is able to make predictions on unseen data. And we'll go through this process tomorrow as I talk through like the structure of your project. But at this moment, any questions? I know we're a little bit over time.
So is the train set on the line, on the regression line, and the test set is your actual data points that you're comparing them to, or is it the opposite of that?
So the y-hat train and y-hat test are for the train and test set on the line. The y train and y test are your actual values that you're given.
Okay, so let's see. So what exactly, so y train is?
Y train are your, yeah,
your
is 80% of your y value. So y train.
Okay. So here. Okay, so essentially y test is the actual values that you're given as y, your actual y values. Train is then the estimated 80% of that, so you can create the model. And then y hat is the regression line, and then you're taking all of, when you run your prediction for your mean squared error and everything else, that's the error between where a point on that regression line would be compared to the train and test. Okay.
Yeah. Anything else?
Nope, that's okay. That makes more sense now.
All right, awesome. I gotta head to a bunch of one-on-ones, but any questions that y'all have on this, Slack me and let me know. I'm actually gonna tomorrow go over what the project structure is going to look like. I think that will be helpful in like helping scope out like who's doing what, especially in your pairs. So I'm gonna be following the project guidelines doc very closely, which is on your homeroom. Right, well, I have to go to the next one-on-one, but I will talk to you all tomorrow at this time. Have a great rest of your day, everybody. Bye.